Hu and Lance Young. Lance is with the University of Washington, and Eddie is with Rice University. So the P measure is a very popular measure of the level of private information for a given stock. It has been widely used in corporate finance, asset pricing, and accounting literature. The problem, however, is that there's some recent evidence that thing doesn't work exactly as we expect. Specifically, there are 2 papers out there that show that thing is higher after public announcements than before announcements. That call into question the validity of this measure. In this paper, what we try to understand is why does Penn fail? And that is an important question because if you want to build on Penn to come up with a new proxy for private information, you want to understand what is actually driving this failure that has been documented in the literature. And specifically, we divide that question in 2 sub-questions. First, we try to understand if Penn fails because it does not match the underlying data well. So the Penn measure is based on a model of the order flow data, of the number of buyer and seller initiated trades. And so if that model does not fit the underlying data, the order flow data well, you would expect that Penn is not going to be a good measure of private information. And so if that is the failure in the model, that's what's causing the failure of the Penn measure, then it's more of a case of trying to come up with new models that match the order flow data better. On the other hand, another possibility is that the order flow data itself does not reveal private information. And so in that case, we need to come up with models that build private information measures based not only in order flow, but in some other variables, for instance, returns. So to address these questions, we pretty much compare 3 different models. And so the first model is the Penn model that has been developed by O'Hara and a few co-authors. And in the Penn model, essentially what we have is 3 like these. The order flow data, the number of buyer-initiated and seller-initiated trades in this model are distributed according to a mixture of Poisson distributions. And in any given day, there is a probability alpha that there is a arrival of private information. And if there is private information, it is good news, the number of buys increase. It is bad news, the number of sales increase. And if there is no news, both the number of buys and sales remain relatively low. So essentially, the Penn model is identifying the arrival of private information from the absolute value of buys minus sales, right, from the order imbalance. So that absolute value increases when there is private information according to the Penn model. The second model that we look at is we call the DY model, and that has been developed in a paper that I have with Lance. And that's an extension of the Penn model. And in that extension, essentially what we try to accomplish, we try to match the order flow data better by creating these shocks that we call symmetric order flow shocks. So these are shocks in which in some days both number of buys and sales increase, so entire volume increase, both buys and sales increase. And it turns out that when we look at the data, including these symmetric order flow shocks is very important to match the majority of the order flow data for the majority of the stocks that we observe. So that's our extension. And it says that the model is still based on the idea that private information is identified from the absolute order imbalance. So it's essentially the same identification as the original Penn model. The third model that we look at is a model that has been developed by authors White and Reddy and Jeffy paper in 2008. It's essentially an extension of Kyle. We call it model WR. And the OWR model is very different from the Penn and the DY model. The OWR model essentially is based on this idea that there is this arrival of private information probability alpha here at the beginning of the day, and And then during the day, the informed traders and the liquidity providers, they trade. And then we will actually observe order imbalance, which is represented here by YE, and intraday return, which is RD. And then overnight, then you see that that private information that came here at the beginning of the day actually becomes public information overnight. And so we actually observe a return, which is this overnight return. So the idea of orders white and ready is that to identify private information, we need to look at the covariance matrix of these intraday return, order imbalance, and overnight return. And they say essentially that when there's private information, that covariance matrix is different from the covariance matrix when there is no private information. Specifically, what they say is that the variance of the order flow, the order imbalance, and of the returns increase when there's private information, and the covariance between these variables also increase. Perhaps one way to understand the equation is to actually look at the covariance between the intraday and the overnight return. So when there is private information, the intraday and the overnight return, they're going to have this positive covariance, essentially because you're going to have a continuation on returns. On the other hand, when there is no private information, we might actually have a reversal in returns. So during the intraday, just the liquidity shock that's not related to information, nothing happens overnight, so you actually have a reversal. So essentially, the Others white and ready model is identifying private information from that covariance matrix, right? The order imbalance, intraday, overnight returns. So essentially, it's identifying private information from the squares of those variables and their interactions. While in the P and the dy model, the identification comes from the absolute order imbalance. And so by comparing the P and the dy model, we can understand that if we have a model that matches the order flow better, how helpful that's going to be to improve on the measure of private information. While by comparing the OWR with the P and dy model, we may actually have some idea of how important it is to include return information when we actually build these measures of private information. Now, to compare these three models, what we do, we use what we call CPI. It's the conditional probability of an information event. And so imagine that we estimate all these models, and now we observe the data for a given day. So observe the order flow, the number of buys and sells for a given day. So based on that numbers of buys and sells for a given day and in the model parameters, we can actually calculate the conditional probability that there was an information event on that day. So that is a daily measure of information asymmetry, of private information for a given stock. And it's based on each one of these models. So we built the CPIs for all the stocks and all the days that we have in the sample. And based on the CPI, we test this model. And we have two types of tests. One type is a regression test. And so essentially in the regression test, we regress the CPI, let's say, of the P model on the absolute order imbalance and the absolute order imbalance square, just to account for some possible nonlinearities. And the idea is that under the P model, when there is information, order imbalance is going to increase, and the CPI is also going to be increasing. So as a result of that, under the model, this CPI variations should be highly explained by the order imbalance. On the other hand, if CPI is varying for reasons that are not related to the order imbalance, perhaps because the model doesn't fit the data well, then we are not actually, in this regression, the CPI P is not going to be actually highly explained by this absolute value of the order imbalance. Now, to test this hypothesis, right, that the P and CPI should be largely explained by the absolute value of the order imbalance, what we do, we estimate this P model for every single stock year that we have in our sample. And then we simulate 1,000 samples for each one of those stocks. We run that regression 1,000 times for each stock. And then we build a distribution of the R-squares under the null that the model is actually truly describing the data. And based on that distribution, we build a test to see if in the actual data, the absolute value of the order imbalance explains the variation of CPI or not. So the results, here's for the simulated data. And for the simulated data, what essentially we see is that absolute order imbalance explains a tremendous amount of variation on CPI P. And all of these is the simulated data, so that's the model. And so the median R-squared is about 80% on average. And if you add turnover, which is number of buys plus sales in this regression, the incremental R-squared, the increase in the R-squared is relatively small. And again, this is under the null. This is the simulated data. Now, in the actual data, on the other hand, this story is very different. In the actual data, what we see is that in practice, the P model is not identifying private information from the order imbalance. The R-squares here, the median R-squares are about 35% in 1993 and about 17% in 2012. And so under the P model, these R-squares should be super high, should be about 85% or so. But in the data, they're much smaller. And so CPI is varying for reasons that are unrelated. What the P model says should be related to private information. And specifically, if you put the turnover on this regression, now you see that turnover is explaining a tremendous amount of variation of CPI P. So the incremental R-squares are about 36% in the beginning of the sample and about 45% in 2012. So what is going on here? What is the intuition for this result? So to understand the intuition for this result, we plot this graph for Exxon 1993, where here we have the number of sales, there we have the number of buys. These clouds here are essentially simulations. So it's simulating the model. And so this cloud here is essentially when there's no information. This cloud of dots over here is when there's positive information about the Exxon. This cloud over here is when there's negative information about the Exxon, right? So the number of cells increase, the number of buys increase when there's positive information, the cells increase when there's negative information. The crosses are actual data. Crosses are actual data, and the pink crosses represent CPIs that are very close to 1 or essentially 1. So it's the model is saying there's probability equal to 1, there's information on this given data. And the blues are essentially saying that this probability is essentially 0, that there is information in this data. So what is going on is that there are all these points here in the middle that the P model cannot classify, because this P model does not allow for volume to increase without the order imbalance not increasing. So anytime that the volume is high, the P model says, hey, must be information arriving in the market. Right? And so that's why CPI P is actually varying more with turnover than with absolute order imbalance. So it comes from a failure of the model to fit the data. How this picture looks like in 2012? Well, it becomes even more extreme. Those 3 large clouds that we saw in the previous picture, now these are these 3 little dots over here. And the level of sales, the level of buys increase tremendously. And essentially you have a 45-degree line. What the P model is doing is saying, hey, every day where there is turnover above the average, there is information probability 1. Every day where turnover is below the average, there is no information. Probability information is equal to 0. And so, perhaps another striking feature of this picture is that most of the points that are outside these 3 little dots over here, the P model associates a probability of 0 for most of those points. That's what that picture is saying. So it's a probability of 0 of observing those specific data points. And you might say, oh, this is just about exon. And so to figure out if this is some problem that happens on many stocks, what we do is essentially go out there and count for every single stock in our sample the number of days that the probability of observing that order flow is smaller than 10 to the minus 10, according to the Penn model. And the bottom line of this picture is that after 2006, for the median stock, the Penn model says that 90% of the days of the median stock have essentially 0 probability of happening. And so I have to wonder, how come that a model that cannot even explain the existence of the order flow can possibly infer if there's private information or not? So I'm going to be briefly with respect to the results of the DY and the OWR model. Turnover also explains a significant part of the DY-CPI variation. The DY model also breaks down after 2006 in the same way that it's the Penn model. The OWR model, on the other hand, seems to identify private information in a way that's consistent with the underlying model. Now, our second type of tests are event study tests. And so here what we do, we use a sample of M&A targets, M&A target announcements, and we plot the CPI around those announcements, an event window of minus 30 to plus 30. And we have two tests for these event studies. The first test, we want to understand if the variation of CPI around the merger's announcement is consistent with the model. In other words, if CPI pins vary around merger's announcements but order imbalance is not, it's because there's something else that's driving that variation that's not related to private information according to the model. Our second test, on the other hand, is we want to see if the CPI in one of these models is higher before the announcement than after the announcement. And that second test is essentially based on this working hypothesis that private information should be higher before announcements than after announcements. And so here's the picture for the CPI pin around mergers announcements. So CPI pin is about 55% in the beginning of our event window, goes up to 0.8, and then comes down. After the event, it kind of comes down slowly. It's actually somewhat higher than the before the event. And when we look at this picture, we might say, well, look, maybe the model is actually identifying private information. It looks like it's detecting something. The problem, however, is that we need to understand where that variation comes from. To understand where that variation comes from, what we do, we regress the CPI around the event window on order imbalance, and try to see how much of that variation is coming from order imbalance. And we regress the CPI in the event window with turnover. We want to understand how much the variation is coming from turnover. And so here's our results. So this line, this dashed line here, is the CPI pin, is the same graph that I showed before. And the continuous line is the predicted CPI pin with absolute order imbalance. So we don't see much of a variation. So pretty much, absolute order imbalance is not explaining much of the variation CPI pin around the event window. On the other hand, the prediction of the turnover is really very striking. So most of the variation CPI pin around the event announcement is coming from turnover. So that calls into questions. There are a few papers out there that run event studies like this, and so it points out that just graphing CPIs or daily measures of private information without actually understanding where that variation comes from can actually be misleading. What about the OWR? So the results of the DY are really very similar to the results of the PIN, so I'm just going to skip those. With the OWR though, it's somewhat different. First, the CPI OWR increases before the announcement, 2 days before the announcement is actually the increase that's statistically significant. Then the day of the announcement is pretty high, day after the announcement is slow, and then it drops very quickly. So that's somewhat consistent with our notion that information is higher before the announcement, then private information should be smaller after the announcement. Even though there is this statistically significant increase, the economic significance is somewhat small. And so that may be a result of the fact that it's very difficult to detect private information in the market. So where this variation of CPI WR comes from, it does not come from order imbalance, and in fact comes from returns squared, intraday returns squared, and the interaction between intraday and overnight returns. And so that supports the notion that if you want to build measures of private information, you need to go beyond just looking at order flow data. You need also to include returns data. So in conclusion, the Penn and the DY models mistakenly associate the variation turnover with the arrival of private information, even when orders are balanced. These models, they break down due to the increase in volume and to the variability of volume that happened specifically after 2006, or mostly after 2006. The OWR model seems to be working well, and when under this working hypothesis that information asymmetry is higher before an announcement, the OWR model seems to be identifying information better than the P and the DY model, and it suggests that order imbalance alone is not sufficient to build measures of private information.
Thank you for inviting me to discuss this paper. This paper, the idea is very straightforward. What the authors are doing, they compare 3 models of information asymmetry, and they're trying to see how well those models are capturing what they intended to capture, which is information asymmetry. The 3 models that the authors focus on are probability of informed trading, originally developed by Edwin and Hara. Its variation that takes into account spikes in turnovers, this is the DY model, and somewhat unrelated model, OWR, that looks at price response to order imbalance. So let me just summarize in a nutshell the key characteristics of each model. The underlying process for the first 2 is Glossner and Milgram, the last one is Kyle. Now, each model has very different parameters. However, what is common for all 3 of them is that all the model assumes that there is a probability of an event. That is, every trading day can be potentially identified as the one that has news and the one that has not. In terms of estimation, the first 2 models rely on the number, on the absolute number of buys and sells in a given day. As opposed to that, OWR, in addition to looking at the order flow imbalance, also look at the returns, both intraday and overnight. How did the authors take it into to empirical test? In order to be able to compare the models, they do a certain extension. They introduce something that is called CPI. And the way they do it is the following. First, they estimate all the parameters of all models for every stock year. After that, using the parameters for a given day, using the number of buys and sells, they look at what is the probability of an event on a given day. So I think if we translate this intuition into a OLS setting, it's somewhat equivalent to Y hat. I obtain parameters of the model, I throw in my X variables, and I get my Y hat. So this methodology allows the authors to calculate for every stock day the probability of having an event on that specific day. And after that, after they have this data, they take it to empirical test. What are they looking for? First of all, they want to make sure that each model indeed captures information asymmetry, what it is constructed to measure. At the same time, they want to ensure that the model does not capture other things that are unrelated to the model. And what they find is the following. Overall, they do find that Penn and DY model, when they look at order imbalance, the coefficient and the explanatory power is out there. However, whenever they add turnover, turnover becomes the most explanatory component. At the same time, OWR model is the only one. OWR model is the only one that both capture the scaled order imbalance, something that is intended to capture, but also does not capture turnover. So the conclusions that the author draw is that because of this pattern, Penn model is not a good way to capture information asymmetry, and instead we should be using OWR. So where do I want to focus my discussion on? First of all, I think this paper is important. Why? Because overall we don't need to even be big fans of market microstructure to end up using the Penn model. It is a common control variable for information asymmetry in different areas of finance. However, it is very easy to just download Penn and throw it into regression. It's much more difficult to try to sort through all the literature and all the evidence that we have on Penn and its extension and to try to figure out whether it indeed works. It's a lot of work, it's a lot of hard work. Jefferson told me yesterday that he has a special room at Rice with 40 different computers, and everything that those computers do is calculate Penn and parameters of the OWR model. So those of you who want to replicate it, good luck. Where do I want to focus my discussion on is the following. The main result is that since C-pi of Penn captures a lot of turnover, Penn model does not work. I think this is a very strong statement. And by saying that, we are somewhat throwing away the baby with the bathwater. That's why what I want to focus on is what does it really mean having this result for the original Penn model. The second point that I would like to make talks about what happens to Penn after 2000. Jefferson has shown that the results are much more severe, much worse when we look at Penn after 2000, and I will talk, if I have time, about what happens out there. So to start, to give you an introduction to the first point that I want to make, let me show you an evolution of a good core study over time. Typically, when we have a core study and it is good, people start replicating it as extended. However, essentially, over time, we get extensions of extensions of extensions, and if you look at any blue point here, it may have very little to do with the core study. So therefore, it's very important to figure out this mess and see what works and what doesn't. However, what happens if you have evidence against? If you have evidence against, we may have two things going on. One thing, it can be evidence against the original model. And this is really bad, because then it means that probably both the model and everything that comes out of it is wrong. However, it is quite possible that what we have is evidence against certain subset of extensions. It's also important news because it allows us to eliminate a certain set of studies that are not applicable. However, we can still maintain the core study and some of the extensions that still hold. And my point here is that what I think the authors find is consistent with case number 2. The fact that C-pi has such huge correlation with turnover does not necessarily mean that the original Penn model does not work. And to try to convey this point, let me look at 3 things. I want to look at the frequency, I want to look at the modeling issues, and I want to take another look at the correlation with turnover. So let me start with the first idea of C-pi. This is not part of the original model. This is something that this is a novel methodology that the authors do here. It makes a lot of sense, it's very intuitive. However, it may be very different from what the original Penn model had in mind. Why? Because what we are doing here, we are switching from annual frequency over which the original Penn model is estimated to daily frequency. And it is quite possible that when we look at covariance matrices among different variables, they behave very differently from annual to daily frequency. I was not as diligent as Ryan to do replications of everything, so that's why I just decided to come up with an example unrelated to finance. Consider the following case. Suppose in true life, my happiness can be explained by how much exercise and the weather. Sunny days may mean happier. Now, what happens if I try to estimate something like this using annual data? In this case, if let's say exercise is persistent, some people always work out, some people never. What I will be capturing a lot of cross-sectional variation across people. However, if all of them come from, let's say, northeast, where weather sucks equally, we are not going to find any impact on happiness. At the same time, if I switch into monthly frequency and I follow a person over time, I might as well find that in June he's happier than he is in January because I capture a lot of variation in the weather. But in this case, I may not see effect due to exercise. Therefore, I think that what happens in PIN model is somewhat like exercise. If it's somewhat persistent across stocks, and I think this is how Isley and O'Hara in fact view it. This is asymmetric information is somewhat a persistent feature, similar to size, similar to PPE, that does not really vary that much. So therefore, it's no wonder that we are not really finding that it's not working on daily frequency. My next, excuse me. My next comment has to do with modeling. The authors show that a shortcoming of PIN is that it does not really work well around events. Now, what happens around events? And I cite this paper not because it's the most important one, but because it was released early enough for Isley and O'Hara to be able to address it formally in the 2008 papers. And what they show is the following. The variation in trade occurs in short periods, and therefore PIN does not capture that. What they do, they change the model, introduce dynamic variation, and they find that the results hold. So therefore, it is quite possible that PIN does not capture those events because the model is too big to capture those short-term things. Lastly, I want to take another look at a correlation with turnover. The authors show that it's very severe. So what I have done, I have gone to the original PIN paper and I have looked at what do they have to say about turnover. And when you look at correlation metrics there, you see that it's not that bad. It's minus 0.3. In addition to that, it's negative. So it's another way to show that covariance metrics may behave very differently from annual to daily frequency. Also, they show that PIN is still pricing returns, for example, after we include turnover. So it's not that bad, and it does not really kill the results of PIN. Let me say a few things. I'm running out of time. Let me say a few things about the result that PIN does not work after 2000. So what I have done to prepare for this discussion, since frankly I have not done microstructure in quite some time, I went back to the notes that I have taken when I was a PhD student at Cornell. And interestingly enough, I found comments from the discussion group that we had with Marina O'Hara, and it was on the DY model, which back then was still a working paper. And I just typed what I have in the notes. Maureen says that many times PIN does not converge for large stocks and huge amount of data. I'm surprised how those guys got convergence. Okay, comments to Maureen. Now, if you think that for whatever reason I made it up, here is some indirect evidence to show that these guys are pretty uncomfortable with estimating PIN after 2000. In fact, what they do is instead, they switch direction, and instead of trying to get PIN work, they look at something very different, VPIN, which looks at toxicity of order flow, but does not require estimations. Why would PIN not work? It would not work because the trading environment these days is very different from what it used to be in the 90s when O'Hara and Isley first estimated the model. These days, markets are fragmented. We cannot just look at how many buys and sells we have in New York Stock Exchange. A lot of trades is happening elsewhere. Second, we have high-frequency trading and we have algorithmic trading. Both of those characteristics allow informed traders to split their orders into small pieces and gradually feed them so that they are not going to affect the prices that much. Therefore, given all of those developments in the trading environment, it's no wonder that PIN does not work. The only thing it relies on is the absolute number of buys and sells. As opposed to that, the reason I think why OW our model works is that in addition to order flow imbalance, which is also scaled, they also look at returns. And returns are always a good representation of what is going on in the markets. Therefore, to summarize, I think that this is an important paper, and the results are very important because they try to figure out what we can use and what not. What I think my take on finding is that PIN is okay, you just need to be careful when you use it. It's good, it's okay if you use it before 2000, it's probably in its original sense, it's not well suited for event studies, but if you want to do something, if you want to capture information asymmetry, probably we need to move on and, let's say, look at OWR model if you want to use data after 2000 and short event studies. So this is my take on the results. This is it. And actually, since I'm the last person speaking here, I would like to take this opportunity on behalf of all the people attending to thank the organizers for doing such a fantastic job and putting together such a great conference, feeding us well, entertaining. We're all having a great time. Muchas gracias.